8.4 is on trigonometric substitution, otherwise known as Trig Sub. So this is basically making use of trig and trig identities to simplify integrands that have like radicals in them. So what we're looking at is integrals involving this form. Okay, so integrals involving these roots. And basically it's like Pythagorean triangle roots concept. So we have things like the square root of a squared minus u squared, the square root of a squared plus u squared, or reversing the first one, the square root of u squared minus a squared. And so where u is a function of x, where u is a function of x, a is constant. So we will also make use of identities. So we have, of course, the Pythagorean identity. So sine squared theta plus cosine squared theta equal to 1. And then you can solve for either of those and get like cosine squared is 1 minus sine squared and stuff. And then we have the secant, so secant squared theta equal to 1 plus tangent squared theta. So all of these you're familiar with. I'm just writing them down so in case we need to use them and just look them up again. Okay. And you can, again, solve for either case when needed. That's pretty much all you'll need. Okay. So then you have these possibilities. You have one. So the first, well, their order doesn't matter, but just we'll have 3 different cases to look at. Basically, it'll involve sine, tangent, or secant. And so if you have the square root of a squared minus u squared, then we're going to draw in these right triangles as such. And I didn't want to make that a equilateral triangle. I think that's close enough. Oops. Should have these all ready to go beforehand, huh? 1, 2, 3, 4, 5, 6. Okay, so not quite equilateral. All right, so I'm going to copy that 3 times. And we will use these down here as well. Okay, I didn't do that in right order. Let's just do it like that. Duplicate, and we'll do it like that. So what you're looking at then is if this angle is theta and you have that right triangle, and this is u and this is a, then this would be the square root of a squared minus u squared. So it all boils down to that radical and what it is. In this case, we will use a sine theta is my u over a, or I'll solve and have u equal to a sine theta. Okay, so that's one form, and then we will do this manipulation of the radical So this is kind of all ahead of time of what you'll be able to do. So then I end up looking at the square root of a squared minus u squared equal to the square root of a squared minus a squared sine squared theta. When you substitute in, this is kind of the point to simplify it down. So that's the square root of a squared, which technically is absolute value of a, but we're talking about a length when we do these. And then it's squared anyway, so. And then that's the square root of 1 minus sine squared theta. And that is, so what is 1 minus sine squared theta? That is cosine squared theta. And so we get this equal to a cosine theta. So we will be able to reduce the radical down to that. And then we'll be able to do the integral better, or more easily, I guess I should say. Okay, so then the next case is case 2. If you have the square root of a squared plus u squared. So if this is theta, and then what that means that the hypotenuse will be the a squared plus u squared. And so this would be your a, and this would be your u. So that one is a tangent. So tan theta is equal to u over a, if and only if u is equal to a tan theta. Okay, last one. Last form of our radicals. We put the radical over here. Square root of u squared minus a squared means that a is here and u is here. And then this is still theta. So that's case 3. Square root of u squared minus a squared. And so for that, what we would have is we have that cosine of theta is equal to a adjacent over hypotenuse over u. So u is equal to a over cosine theta. So a is secant theta. U equals a secant theta, sorry. All right, so we can use those. Now let me show you how this is manipulated. Let's look at an example. We'll just go down here and come back up to it. So suppose you have this case. Evaluate the indefinite integral of 1 over square root of 4 plus x squared dx. And so right away, if you have a sum, it's going to be this case here. So we'll be looking at all of this stuff. Okay, so, oh, you know what? I'm going to show you this too. So for, we'll get there in a second. Okay. So then what you have, you want to draw in. So for trig sub, I'll usually will say use trig substitution, because you end up deriving formulas and stuff. So this is what I want you to do. Use trig sub to do this, and you want to draw on your triangle. You want to show what you're doing using the triangle. Okay, so here's my right triangle. This is my theta. And so this hypotenuse has to be the 4 plus x squared. That's my u, and then this is 2. Right, of course, because a is equal to 2, and my u is just x. All right, so then what I end up with is that tangent theta is equal to x over 2 if and only if x is equal to 2 tangent theta. So if x is that, this is when you have to do your dx. So then dx is equal to derivative of tangent is secant squared, so it's 2 secant squared theta d theta. So that's what we're looking for. That will be our, so your dx is here. So that ends up being all of this, 2 secant squared d theta. But you want to, the whole goal really is to eliminate this radical. So now we got to substitute into the radical. So substitute into the square root. So we'll come down here, we'll say the square root of, and so that's 4 plus x squared. And so now we have that our x squared is 4 tan squared, and then we'll do our trig identities. Okay, so this is a good place to pause and work this out on your own. You get 4 plus 4 tan squared theta. So 4, and then that's just 1 plus tan squared theta. And so this is secant squared. So that's 2 times the square root of secant squared theta. So that's 2 secant theta. So you get 2 secant theta. So that's the manipulation that you end up doing. That's just like doing this one here when you substitute. So all of these have their equivalent substitution into the radical to simplify it. I just didn't show every case because we're doing it right now. So we go ahead and substitute, and so this, I'll bring that down, equals the integral, and then our denominator, so we worked out that denominator, so that's 1 over 2 secant theta, and then my dx is all of that mess, so that is where am I at? I'm sorry, here it is. Okay, so that's this. So that's 2 secant squared theta d theta. Simplify, and you get secant theta d theta. And that's one you may want to look up. It's kind of messy. So that is equal to the natural log of absolute value of secant theta plus tangent theta plus c. At this stage, we need to substitute back. So now substitute for theta and write in terms of x. So we have that. We got to find out what. So now you go back to the triangle. So go back to the triangle. Go back to the triangle, which is here, right? So here's my triangle. So what is secant and what is tangent? So the secant theta is hypotenuse over adjacent, right? So it's the square root of 4 plus x squared over 2. And tangent is opposite over adjacent, so x over 2. Okay, so now I can substitute in, and I get, I'll just bring this down, that equals then natural log absolute value of secant, which is the square root of 4 plus x squared over 2, plus x over 2, plus c. Okay, so now a couple things we can do. I mean, that's pretty much it, although we can manipulate this a little bit. So let me show you this. Let's see, where was I at? Generally speaking, that's fine, but check this out. So since, it's supposed to be capital, but since the square root of 4 plus x squared is always greater than or equal to x, we essentially can drop the absolute values. This is equal to natural log of absolute, oops, that's what I meant to do. We can drop the absolute values, so you just get this, and I'm going to factor out that half. So it's the square root of 4 plus x squared plus x, and then it's times a half. And so, because of properties of the logarithm, I end up with ln of the square root of 4 plus x squared plus x plus natural log of a half plus c. So I can make this now my arbitrary constant, call it d. And so this equals natural log square root of 4 plus x squared plus x plus d. Okay, so I'm using this property of logarithms for just that product right here, this product. So anyway, it can be simplified a little further if you make a little argument here. Okay, let's do another one. This one will be next example. Evaluate the integral of the square root of x squared minus 9. So I had to change that up, right? Over x dx. Okay, so now we need to figure out our our triangle in this case. So you go back and you see which case. You remember it was u squared minus something. So it has to be this case. It's the variable and then the constant. So it's this case. So then you know where to plug it into. Okay. So let's write that triangle down. I have to go faster, I guess. Okay, so that's the square root of x squared, oops, not a plus, x squared minus 9, and then my a would be 3, of course, and my u is just x. Okay, so now let's simplify the radical. So the radical square root of x squared minus 9 is equal to, and we're using all of this again. Okay, so we know that u is secant squared, or x is 3 secant squared. We're going to use that. Okay, and you can always reproduce it here if you want. So that's the square root of 9 secant squared theta minus 9. And so that's going to be 3 square root of secant squared theta minus 1. Bring that over like that. So that has to equal 3 square root of tangent squared theta, which is just going to be 3 tangent theta. So now our x, we have that our x is 3 tangent theta. So then we have to do our dx. Our dx then was going to be, so derivative of tangent is secant tangent. So it's secant theta tangent theta d theta. I'm fixing my notes. Got the d theta in my other notes. So we have everything we need now to substitute. So the radical becomes 3 tan theta. The dx becomes all of this. So that's what you're substituting. So all of this is this. We do need to substitute for x. So x will be this. And then my dx will be all of that. Okay, so let's do our substitution. Okay, so we have the square root of, integral of the square root of x squared minus 9 over x dx is equal to, now let's substitute everything in. That's the square integral. So all of that stuff up top became what? 3 tan x, so that's 3 tangent theta, theta, over, denominator is going to be just my x. Wait, I messed up somewhere. Let's see. This is secant. Yeah, this is secant. Okay, so this needs to be fixed. X, when I solve this, I have that secant is hypotenuse over adjacent. So x is 3 secant theta. So dx is that. Okay, so that's better. 3 secant theta. So derivative of secant is secant tangent. Not tangent. Derivative of tangent is secant squared. Okay, so now we have that better finally. Okay, so now my root is the 3 tan, and my x is 3 secant theta. And then substitute for your dx, 3 secant theta tangent theta d theta. And we simplify. That simplifies down to just the integral. So that's going to be 3 so 3 tangent squared theta d theta. Okay, so now we can simplify this a bit. So it's 3 integral of secant squared theta minus 1 d theta. And so that's 3, well, we can just do it right. It's pretty much there. So secant is tangent. Secant squared is tangent. And then you get a 3 theta. So we get 3 tangent theta minus 3 theta plus c. Now we substitute back. So secant theta is x over 3. I'm getting that from the triangle each time. I'm getting it from here. And we have that tangent theta is opposite over adjacent, so it's the square root of x squared minus 9 over 3. And we're going to need theta, so theta is equal to secant inverse of x over 3. So we have that the integral of the square root of x squared minus 9 over x dx is equal to, substitute back in, you get the root of x squared minus 9 over 3 minus 3 secant inverse of x over 3 plus c. So I'm just substituting for tangent here. It gives us, you got to go back, and then your theta was isolated as well. So I just took this and solved for theta, and then now I substitute it back into there. Okay, so you're taking it out of x into the trig stuff, and then you're putting it back into the x, like if you want to think of it like that. Okay, that is a couple good examples in 8.5. Now we go on to tables, which can be interesting. So we'll get to that. So practice more of these. Definitely be one of these asked, and setting up the triangle and all that kind of stuff. Okay, so that's what we covered.